Welcome back to our study of linear equations, looking at a mechanical system, a 50 Newton weight supported from a horizontal beam. In this session, we're going to look at the solution using matrix algebra, then we're going to follow it with a solution using Cramer's rule. To this point, we have solved the problem using one technique. We use substitution, and we saw what values we got from that. We're going to skip on the graphing technique, and in this lecture we're going to look first at matrix algebra as a way to solve the suspended box and the tensions on the cables. Then we'll use Cramer's rule to solve it. Using the substitution technique, we learned that the tension on the cable at 38 degrees was 36.6 newtons, and the tension on the cable that was suspended at a 45-degree angle was 44.82 newtons. Now let's go on to matrix algebra and see if we come up with the same answers. The first thing we'll do is set up our equation again. We know that the tension on the first cable times the sine of 30 degrees plus the tension on the second cable sine of 45 degrees gives us our vertical load of 50 newtons. Similarly, the tension on the first cable at a cosine of 30 degrees and the tension on the second cable at a cosine of 45 degrees. Now remember, they're pointed in two different directions, but the horizontal forces sum up to 0 while the vertical forces sum up to 50. We go back to our typical matrix solution statement. The matrix A times the unknown vector equals a result vector B. And here's what it looks like in our problem set up in matrix format. Here we've got our sine of 30 degrees. We've got our sine of 45 degrees minus the sine of 30 degrees, or cosine of 30, and the cosine of 45. Those are our matrix for the A terms. Our unknown are tensions 1 and tension 2, and our result vector is 50 degrees vertical, 0 newtons horizontal. So reducing that from sines and cosines to numerical values, this is what we end up with. Well, let's go back and real quick review what we saw in the previous lecture regarding matrices. Matrix A times the unknowns gives us vector B, the result vector. There's A with its 4 points, A, B, C, and D. The solution is equal to the inverse of A times the result vector. And the inverse of A is calculated by taking 1 divided by the determinant and multiplying that by a transposed version of the original matrix, where we swap A and D and we change the sign on B and C. The result tells us that delta, the determinant, is going to be A times D minus B times C. Now this is a definition, and that comes back to this matrix. Interestingly enough, it will work on this one also because we've changed both signs to negatives, and it's still AD times minus BC, but that's the definition of the determinant. So now let's put it into matrix format. A is going to be 0.5, 0.707, minus 0.866, and 0.707, as we've already determined. Delta AB minus CD works out to calculated to 0.9659. 1 over delta then will become 1.035. We know what our matrix was. Now we need to calculate the inverse of our matrix in order to solve the problem. Okay, let's finish the calculation. We know that the inverse is 1 over delta times the matrix D minus B minus CA. Here are the numbers plugged in that we've already calculated, so that the inverse matrix is each of the values divided by each of the matrix values divided by delta, and that works out to these values. So that is the value of a to the minus 1. To this point, we've determined what our inverse matrix looks like, and we already know what our output result vector looks like, so we can now multiply the inverse of our matrix by the resultant vector. Here's the pieces, and when we do that, we find that the tension 1 is 36.60, tension 2 is 44.83, and matches what we figured out as we calculated the same result using substitution. Now let's look at it from one more angle, and let's use Cramer's rule. Using Cramer's rule, we again start with a system of equations. Our matrix A times the unknown vector x equals the result vector B. So our solution using Cramer's rule is calculated that the first unknown, x1, is going to be found by replacing the first column of our vector A with the result vector and finding its determinant, and then dividing that by the determinant of matrix A. Similarly, the second unknown will be found by calculating the determinant of a matrix with the second column replaced by our result vector, and again that divided by the determinant of matrix A. So solving for x1, we take, and the result vector 50, 0 is substituted into the first column. The second column remains untouched, and we calculate the determinant. 50 times 0.707 minus 0 times 0.707 will give us 35.355, or 35.36. The determinant for matrix A comes out to 0.966. Again, 0.5 times 0.707 minus 0.866 times 0.707, but the 0.866 is already negative, so that becomes a positive, so this becomes this plus this and gives us our 0.966. So 35.355 divided by 0.966 is going to give us 36.60. Similarly, solving for matrix for the unknown, second unknown, we'll take the determinant of our second variation of the matrix divided by the determinant of the matrix, and now we have again substituted in our result vector, but this time in the second column for our second unknown, and we've replaced the first column with the matrix A first column, and we find out that the determinant of A2 is 43.301. We already know the determinant of A, 0.966, so dividing 43.301 by 0.966, we come up with 44.83. And we find that as the other techniques, we come up with the same solutions. So we find that Cramer's rule works very nicely for us. We began our study of linear equations using apples and oranges in order to learn how to solve the equations using substitution, graphing, matrix algebra, and Cramer's rule. Going a little more technical, we looked at a mechanical engineering example. Come on back one more time and we'll look at an electrical engineering example. Thank you, and we'll see you next time.